Beneath our feet, beneath our cities, beneath almost every landscape in the world, somewhere in the soil and rocks that make up the outermost crust of the earth, there is water. This underground water, or groundwater, is not easily observed, yet there is vastly more fresh water in the ground than there is in all the world's lakes and rivers combined. Globally, nearly half the world's population relies on groundwater. Here in South Central Texas, it's the sole source of drinking water for millions of people, and it supports federally protected wildlife. Unfortunately, groundwater systems are notoriously difficult to understand. Vast, complex, and hidden, they demand specialized knowledge of two ubiquitous but surprisingly enigmatic substances, water and rock. What have we, as a civilization, learned about groundwater, and how do we know it? I'm Logan Schmidt, a geoscientist at the Edwards Aquifer 30 in San Antonio, Texas, and this is The Recharge Zone, a podcast where we explore the biggest concepts in South Central Texas hydrogeology. In this episode, I'll ask hydrogeologist Dr. Jack Sharp, what is groundwater? And how can the study of hydrogeology help us manage, enhance, and protect the Edwards Aquifer? Dr. Jack Sharp is professor of geology emeritus at the University of Texas at Austin. He is internationally recognized for his research on groundwater flow in fractured and karstic aquifers, urban hydrogeology, and the Edwards Aquifer. He served as program director for hydrologic sciences at the National Science Foundation, and he's received the O.E. Menzer Award, the Geological Society of America's highest honor in hydrogeology. Jack, it's so nice to speak with you. Welcome to the Recharge Zone.
Thanks. It's a pleasure to be here.
Groundwater is such a broad topic, so maybe we could, and there's a lot to talk about, so maybe we could start with the basics. What is groundwater?
Well, groundwater basically is all water that's beneath the land surface. And every place in the land surface, if you dig down of a well, that well is going to fill up with water, maybe very slowly, but it will fill up. And that level to which it fills is called the water table. So sometimes we talk about groundwater as all water beneath the water table, the level of water in a well.
You've studied groundwater as a professor of geology at the University of Texas at Austin since the 80s and have built quite the legacy there. I kind of wanted to ask, how did you get into this field? How did you get interested in groundwater?
Well, it's really interesting. I grew up in Minnesota. It was never far from lakes or streams. Did a lot of fishing, canoeing, loved water. And I thought about going into geology, but at the time, my dad was a lawyer, and he had the Minnesota State Geologist as one of his consultants. And Dad said to Dr. George Schwartz, "George, my son John likes the outdoors. Should he become a geologist?" And Schwartz said, "No. There's no jobs in geology now. Now, geological engineering there are, and it's one of those times in geology, I guess the oil company was laying people off. So I went into geological engineering and served as a civil engineering officer in the Air Force, but I wanted to get back into water, and I wanted to study nature's systems. So I was fortunate enough to go to the University of Illinois, get my graduate degrees. And it's just been a wonderful adventure. After Illinois, I spent 8 years at Missouri, and then was fortunate enough to come to the University of Texas. And it's been a wonderful adventure. And we learn more and more about groundwater all the time. It's a vast field. We're learning more all the time. We know so much more than we did 20 years ago, and we know so much more that we don't know.
I'd like to talk about some of that stuff that we don't know, and also about your work on the Edwards. But maybe before we get there, I think people are at least passingly familiar with the concept of the water cycle. At least people have experienced rain and know what rivers are. Could you talk about the water cycle a bit?
Certainly. The hydrology cycle, or the water cycle, describes how all water on the earth, above the earth, and under the earth circulates. And it's a basically, on one hand, it's a very simple system. We have the oceans providing most of the water. You get evaporation from the oceans. There's kind of a net transport inland. It falls on the land surface. Some of the water will infiltrate into the soil. Some of it will run off into rivers and lakes. And that stuff which infiltrates into the soil continues to move down till it hits the water table. And that forms the groundwater system that also flows to the rivers and lakes and the oceans. Why do the rivers run when there's no rain? It's being fed by groundwater. And so that circulation is the key. And there's basically a fixed amount of water in the earth. Well, there's a little bit that comes in from comets and a little bit coming out from volcanoes. And maybe we lose a little bit in the upper atmosphere, but it's basically fixed. So we have a fixed amount of water in the earth. It's just recirculating constantly. And that's the challenge. Where is it? So do we have water shortages? Yes, we have lots of water, but it's not always the quality we want or the amount we want where we want it.
So I guess, why do people, what is significant about groundwater? Why do people study it? It seems like it might be hard to access compared to a river or something like that.
Indeed, because you don't see groundwater until it exits from a spring or a well. And that's one of the challenges we have. It was interesting. If you go back historically, people had a hard time understanding how springs actually occur. And people had various explanations going back to the Middle Ages of the under the mountains was kind of like a giant still that was evaporating, and water would come up and exit the springs. But we started measuring it, and we found that there's about 4 times more rainwater hitting a river basin than is actually flowing out of the river basin. So where does that water go? Most of it that hits the land surface evaporates or transpires from plants as the plants breathe and respirate. So one of the challenges we have is it gets hotter and hotter. We're going to get more evapotranspiration, evaporation and transpiration. It's going to stress our water resources.
What makes groundwater systems, at the top, I kind of suggested that it's difficult to understand groundwater systems. Would you agree with that?
Yes and no. The physics, how groundwater flows, we understand that. But the details of how we apply those in the real world are very, very complex. For instance, in the Edwards Aquifer, our understanding of how the groundwater flows in the Edwards Aquifer has changed dramatically in the past several decades. We thought we had the answers back when I first came here in the 80s, and we found that, well, we're generally right, but the details were completely wrong.
So it sounds like you would say, in general, the principles of groundwater are well understood, but the details of applying those principles to any given real life situation, the devil's in the details, it sounds like.
Exactly. You hit the nail right on the head there.
You mentioned this a minute ago, but maybe we could focus on wells and springs a little bit more. You mentioned the water table as well. I think these are the things that people, if they have encountered groundwater, those might be the most accessible parts of groundwater. What's the relationship? Like, what is a well? What is a water table? What is a spring? How are they related?
A spring is a place of concentrated discharge where water flows from the ground to the surface. And typically, most rivers are getting groundwater flow, sometimes in the concentrated places as springs, but sometimes in a more general flow into the systems. So you can have groundwater flowing into rivers even if there's not a spring. But in karstic aquifers like the Edwards, springs are one of the major characteristics. So the wells, and once again, any place in the Earth's surface, if you dig down, you'll find water. A well is one that we can use to take that water out and use it in usable amounts and usable qualities. And so that's the key.
Okay, I want to talk a little bit about something that I think is very interesting, and a concept that I think hydrogeologists have that maybe the public doesn't, is that in my opinion, let's see if you agree. I think like one of the most characteristics aspects of groundwater systems as opposed to other parts of the hydrologic cycle is that they're fundamentally two-phase systems with water as the liquid phase coexisting within a solid phase of geologic materials like rocks and sediment. And I think that's sort of a conceptual hurdle to jump over because maybe people aren't thinking about porous media as the technical term. I'd like to spend some time talking about the consequence of this like two-phase configuration. Can we start by talking about geologic materials? I mean, groundwater is water in the ground. What is the ground? It's geologic materials. So like what are the geologic materials? What is the ground made of that can contain groundwater?
Okay, that's a really good question. First of all, when people talk about an aquifer, it's not a lake.
Mm-hmm.
It is not a lake.
Mm-hmm.
And all rock materials near the surface have holes in them. Sometimes they're cracks, sometimes there's caves that you can walk in, but every rock has got cracks in soil. Everything near the surface has got holes in it. We call those pores. And below the water table, those are all filled with water. And it flows from areas of, I don't want to say high pressure, but it's elevation and fluid pressure combination, and it flows to lower areas. So surface water flows downhill. Groundwater flows down what we call the hydraulic potential. And the hydraulic potential can be measured. It's basically as the elevation of the water in the well relative to some datum like sea level. So we'll talk about wells in the Edwards as being so many 100 feet above sea level, the water table. I wanted to go back a little bit, and there's groundwater because it's hard to see. It was difficult for people to understand, and there was a famous court case back in Ohio in the 19th centuries, which said that the movement of groundwater was so secret and occult that nobody could ever figure it out, and we could not make any laws to govern groundwater based on the knowledge of groundwater movement. This was a legal precedent, and it's still in the books. But we've learned a lot, and I think we can do that now. So the groundwater movement's so secret and occult that nobody can even hope to understand it. False.
I really like emphasizing the groundwater is not a lake, and maybe I'd encourage people to try to imagine maybe when they water their potted plants or their garden, they have the experience of pouring water on the surface of the pot or the ground, and then the water seeps into the ground. And I'd challenge people to imagine where that water is going, what that looks like.
That's very good. And if you put too much in, it comes out the bottom of the pot, doesn't it? Yeah. If you look at an aquifer, like the Edwards, an aquifer is a body of rock that holds water and can transmit it. The water can flow through it in big enough amounts that it can supply a well or a spring. So that's what an aquifer is. And the groundwater flow from elevations where the water table is high to where the water table is lower. It's not flowing downhill, but it's flowing down the hydraulic gradient, which is measured in the wells.
I'd also like to challenge listeners with this concept. Like hydraulic gradient might sound technical and unfamiliar, and it is a challenging concept. What we're really talking about is sort of potential energy, right? Everything in nature, anything that happens spontaneously, something is moving down an energy gradient. And in the case of groundwater, there's sort of different ways of characterizing the energy gradient, but one that people might be familiar is hydraulic head. Could you talk about what that is and maybe relate it to the water table?
Yeah, well, hydraulic head is any point in the groundwater system, if you put a well in, like essentially a straw, the water will rise to some level within that straw. And the more the hydraulic potential, the higher that water rises. And so if you have a well at one point that's got a higher head, higher elevation, and a well next to it or close to it at a lower head, the water is going to flow from the high head to a low head. Think of it, water trying to find its own level.
Mm-hmm.
Now, the rate at which that happens is controlled by permeability.
Mm-hmm.
And some rocks, like the Edwards, have very, very high permeability. The water will flow from an area of high head to low head very quickly. In others, sandy or more silty aquifers where the pores are finer, it may flow much, much more slowly. But it does get there eventually.
So let me see if I can reword what you just said. So water will move from high head to low head, and how quickly it moves or how easily it moves is controlled by a property called permeability. And different geologic materials have different permeabilities, and so the kinds of rocks or sediment that underlie a landscape is going to control the properties of the aquifer, like how much water you can pump out of it.
Exactly. And some aquifers, like the Edwards Aquifer, or some of the sand and gravel aquifers, are very permeable. Water flows much more slowly. Sandstones might like the famous Dakota sandstone of the American West, it would flow more slowly. But even rocks like granites at depths have cracks in them, and the water's flowing there, but very, very slowly. And it's a hard thing to imagine, but if you compare permeabilities from the high end of permeability to the low end of permeability, it goes by what we call orders of magnitude.
Mm-hmm.
And the range of permeabilities in orders of magnitude is greater than comparing the order of magnitudes of our walking slow to the speed of light. Mm-hmm. That's many orders of magnitude, but permeability varies by even more.
And so would you say that sort of huge range of permeability is one of the things that makes groundwater difficult to understand? That's one of the details, right? That makes
yes, mm-hmm. Yes, indeed. And the details of the holes, the pores, is also critical. And sometimes the water will flow in very, very complicated paths. And this is when we found frequently that we thought we knew which way the water was flowing, but as we get more and more information, it gets more complex.
Mm-hmm. So we touched on this a bit. Aquifers are could you just real quick? You already defined aquifer, but I'd like to maybe clarify what's the difference between groundwater and aquifers, and let's start there.
Well, an aquifer is a body of rock that contains water, contains mm-hmm. groundwater, and the groundwater in that aquifer flows to springs or to wells that you're pumping mm-hmm. in amounts that we can use. So it's got to have enough water that it's usable economically, and it's got to be of a decent quality. So an aquifer is kind of interesting. It's kind of like a mineral deposit. Mm-hmm. And if water becomes more valuable, rocks that we didn't think were aquifers, by definition, becomes an aquifer. So an aquifer is the body of rock or soil, could be, or sands, mm-hmm. that contains groundwater of usable quality, and it can provide water to springs or to wells.
That characterization is interesting to me. I found in my experience, I've taken some classes when I was in grad school in the Department of Petroleum Engineering, and maybe have you encountered? I've encountered that people that are experts in exploration geology, trying to find hydrocarbons like oil and gas underground, learn a lot of the same technical skills that a hydrogeologist does. Is there overlap in your experience between the kind of two specialties and professions?
Yes, oil and gas are also fluids,
Mm-hmm.
and they flow by the same basic laws of groundwater.
I think that's interesting that there's laws in the book saying groundwater is so occult, yet oil companies have been making money for a long time, pumping oil out of the ground, and if they have the same physics, it seems like a little bit of a contradiction.
Yes, indeed, and it's the legal justification and the court case that I cited is actually one of the basis for Texas law.
Mm.
When you get right down to it.
Mm.
So basically, we came up with things that, well, if you the water's under your property, you own it, which is the Texas law right now.
Mm-hmm.
But it doesn't stay under your property. It's flowing, some coming in and maybe some coming out. We don't know.
That reminds me of the movie. Have you seen There Will Be Blood?
Yes.
There's a famous scene at the end, spoilers potentially, but the main character is like screaming at another character about like, I drink your milkshake is one of the lines. And I think it's that concept where I think that one of the characters is, he had a property that they hadn't sold to the oil company, and he thought there was going to be this big play of oil underneath it, but all of the property around that, all the land around that property had been developed for oil extraction, and so the main character was trying to convey this concept where I don't have to drill an oil well in this case right on your property to get the oil that's under there, because it'll flow from the property to where I do have wells.
Yes, there's the Texas Railroad Commission is in charge of this, and at one time in some of the basins out in far southeast Texas, people were producing wells, and people said, I'm going to put my well right next to the property boundary, and I'm going to suck the oil out from under your property. And people said, well, you can't do that. I'm going to put another well right, and a bigger well, and pump it. And they were pumping so much out of spite, they were just dumping the oil in the ground rather than let the person at the other side of the property take my oil. And so that's why the Texas Railroad Commission was in charge of what called unitizing the fields and say, we're going to work this out so the resource is shared equitably with the landowners. That's why the Texas Railroad Commission monitors oil and gas production in the state of Texas.
It's very interesting. I think we've talked about a little bit about how, well, you mentioned up top when we were talking about the water cycle that water is really not, the amount of water that's created and lost from the earth is basically negligible. And in my experience, or in my opinion, if there's anything like a unified theory of hydrogeology, it's probably the conservation of mass as applied to water. And a lot of times we'll talk about something, or from that principle, we can kind of treat water like the water in an aquifer like a bank account, and create what's called a water budget. That's even a term that's used in the literature quite a bit. Maybe could you talk about what a groundwater budget is?
Certainly, yeah. Logan, that's a very nice analogy. In every aquifer, there's a certain amount of water in storage. That's all the water that's contained in the cracks and the tiny pores and the cabs, everything. And the aquifer, our geologist colleagues have mapped these rocks very well. We have pretty good ideas of the volume of the aquifer rocks and the porosity, so we know how much water is in there. But there's always water. I should say not always. Some aquifers are very deep and are almost kind of isolated, but most of them have two important things. There is a recharge. That is how water gets into the aquifer. And that can be from the precipitation of rainfall sinking into the soil. It can become from leakage or flow from other units, either rock units that are beside or underneath or above. And that's called recharge. That's the total amount of water going in. Then you have discharge, and that's the amount of water that is leaving the aquifer by flowing to wells or springs, or maybe flowing into other rock units above or below or laterally. So if you think about it as a bank account, the discharge is how much you're spending, and the recharge is how much you're earning. And if you're spending more than you're earning, your bank account goes down. If you discharge more than you recharge, the amount of water in storage goes down.
Where ultimately is recharge, or if to continue the analogy, like maybe in a bank account you deposit money in, and that's coming from, I don't know, you're making money somehow.
Yep.
Where's recharge to an aquifer coming from?
Well, ultimately, it is in the long-term sense, it's almost all precipitation, rainfall. There's a minor amount that comes from magmas and lavas deep down below, and we lose a little bit of water from some of the geologic processes, which I won't get into, subduction and so forth. But it's interesting, and in the Edwards Aquifer in particular, we have 3 sources of recharge. We have water that precipitates, falls on the rock units that make up the aquifer. That's kind of a fancy term. It's called autogenic terms, but it's recharge that's occurring in place. We also have a source of recharge from streams that flow over the Edwards and then sink into the soils. We call that a kind of indirect, or another fancy term, allogenic. So we have water from the streams that flow over the Edwards Aquifer, and the water sinks into it. And we have recharge from direct precipitation. And in certain areas where we've developed, we have water from man-made sources, leaky water pipes, leaky sewage pipes, overwatering of lawns and gardens. And that's generally minor. In the Edwards Aquifer, in years where there was virtually little rain and little stream flow over these areas, that becomes relatively important. In wet years, it's minor.
I'd like to ask now, so I think an interesting difference between a bank account and aquifer is that the kind of money in your bank account doesn't matter. It's all the same thing. But there's this concept called water quality that applies for groundwater systems. Maybe you could tell us what is water quality? What do people mean when they say water quality?
Well, we don't drink seawater. Its quality is not sufficient for that. So there's several things that make up water quality. It's taste, it's salinity, are there poisons in it or contaminants, and so the water quality says, what is the use to which we want to put the water? Is it for drinking? Is it for flushing toilets? Is it for feeding our livestock? And we don't want water that is too salty to drink. We don't want water that has got nasty things in it, contaminants. And we'd also like water that looks nice. So all those things make up quality, and there's a whole series of limits on these things. For instance, you don't want more than so much nitrate in your water. You don't want so much more. You don't want less than. Well, typically we say about 1,000 parts per million is the upper limit for drinking water, and ocean water is 35 times greater than that. Now, if it's for your cows, they can take water saltier than we are. If it's for washing your clothes, you want nice soft water, so your whites are whiter and your brights are brighter. So all those things. And there's the Environmental Protection Agency has a huge list of these things. And remember, everything is toxic if you have too much of it.
Mm-hmm.
Too much fluoride is toxic. Too much salt is toxic. Actually, too much water is toxic, or too much air is toxic if you have too much. So the water quality is what is the use to which you want to use the water, and one of the things people are concerned about now as the ocean levels are rising is, well, the aquifers near the Gulf Coast become saltier. So this would be, and if they become too salty to use, by definition, it's maybe not an aquifer anymore.
What affects the water quality of aquifers?
It's several things. First of all, what's in the recharge water, the water that enters the aquifer. And as the water flows through the soils and rocks, water is the universal solvent. It dissolves things. And as it flows through the rocks, mineral matter in the rocks and in the soils and the organic matter become part of the water. They become dissolved in it. And in some aquifers, as they go through rocks that have halite or salt in it, they become very, very salty themselves. And so when you go to when those aquifers discharge to the surface, you get salt lakes, salt flats.
Could you talk about maybe some? Let's talk about some of those details. Like, what specific groundwater systems have you worked on, or are interesting to you, maybe around the world or in the United States?
Oh golly, that's one of the great things about being a hydrogeology professor. I've had an opportunity to go all over the world on these things. I first started looking at flow in some of the big alluvial systems, like the Missouri and Mississippi River alluvial floodplains. And those are very productive aquifers, and over in the floodplains, beautiful farmlands become very productive. There, the problem has been when the farmers have been putting too much fertilizer and nitrate on, as the water they spread on is used for watering the crops. As that water sinks in, it dissolves the nitrate, and the nitrate can become toxic. It can lead to what's called the blue baby syndrome. That if you have too much nitrate, babies that have drinking water with too much nitrate start turning blue because they're losing oxygen.
Wow.
It was interesting. There was a park in Arizona I was visiting years ago, and it said, "Do not use the water in this well for baby bottles because the nitrate is too high." And then it said, "And don't try to boil it. That's not going to get rid of the nitrate. It only concentrates it." So, but one of the things that we found, at least in my career, is groundwater contamination is much more widespread than we'd ever imagined. Many of the things we put on our lawns, atrazine, what's Scott's weed and seed is one of them, I think. That turns out that's been spread over. We see that in our wells and our aquifers now. Farm chemicals, fertilizers, pesticides, herbicides that we use in our lawns and in our fields. Those don't disappear. Most of those, some can get harbored in the soil and some not. And then another one interesting was gasoline. Now, our younger listeners won't remember this, but it used to be that many of the gasoline tanks at the gas stations were kept above ground. But that turns out that's a fire and explosive hazard. So the solution was, well, let's bury the tanks in the ground. Then it turned out that over time, many of the tanks leaked. So we had, over many gas stations over the world, what we call plumes, or areas of gasoline and dissolved gasoline in the groundwater. And that's just one example. We've spent billions of dollars cleaning up these sites. And then we found that, and the people that were doing these things in the past, they thought they were doing the right thing, but you have hazardous materials, you don't know what to do with them. Let's just bury them somewhere. They're isolated, right? Well, if there is the hydrologic cycle and water flowing through those things, these things can become highly contaminated. And we ended up what we call our Superfund sites, sites that are so highly contaminated. We spent billions and billions of dollars trying to clean these things up.
So it sounds like preventing those contaminations is a very cost-effective way of handling groundwater quality.
Yes. And for instance, the dry cleaning establishments, many years ago, they said, what do you do with the excess dry cleaning fluids? And they said, well, we'll just put them out on the land surface and they'll evaporate. Well, some did and some didn't. So yes, prevention is the best way of doing it.
You mentioned you talked about aquifers and floodplains of big rivers like the Mississippi, and you used the term alluvial aquifers. And could you talk about what alluvium is and what floodplains are?
It's when you go to your doctor, sometimes they use the medical jargon, and you have to get into alluvium just means alluvial means it's related to a river. Alluvium are sediments and rocks that are deposited by flowing water. And so I apologize for that. So if there's any more of those, let me know and I will translate them for you. So, and these are tremendous systems like the Nile River system. Now, the Nile, of course, is a big alluvial aquifer, and the floodplain there was irrigated by floodwaters, but also by wells. So when they're not having the floods, they irrigate with well water from the alluvial system. And it turned out in some places they're getting very, very high manganese concentrations. And this is not a health issue, but it is a drinking water quality issue. It makes the water taste bad. So we are trying to figure out where the manganese was coming. It's coming from weathering by the water of some of the Nile River sediments. And some of them came from parts of Africa where there's a lot of minerals with manganese in them that was leaching out into the water.
Yeah, maybe people haven't thought about this too much, but rivers carry sediment or little bits of rocks, sand, it was a kind of sediment, clay, silt, and rivers deposit that sediment in certain places, and that can accumulate to big deposits of alluvium, and then that alluvium then stores water that people can use for farming and agriculture.
Yes, and some of the most productive lands in the United States are in alluvial floodplains, and so. But even in areas like the Llano Uplift here in Texas, it's rocks that are granites, they're igneous and metamorphic rocks, and typically we don't think of those as aquifers. But in the shallow systems, there are cracks. There's all cracks in these things. Call them fractures or joints, but they're basically cracks in the rocks, and they hold water. And it turns out many places in the earth, these rocks dominate. And so we have to find out how to find water in these places where you may drill a well and the permeability is so tight, it takes forever to fill it up. So if you pump it out once, it's gone. So you have to find where the cracks are with water and where the cracks are connected. And you find those, you can find enough water for a house or several houses.
I think there's something I think about quite a bit, the difference between a fractured rock in terms of aquifer and groundwater production versus unconsolidated sediment like alluvium. And maybe You just made me think, like, drilling a well in a fractured rock aquifer, especially something as tight as granite. It's sort of like you're trying to find a needle in a haystack with that well. You're just hoping that you hit a fracture that you have no idea where. There's no way to know that I'm aware of a priori where the fractures are. I mean, there's maybe ways you could try to characterize it, but it'd be difficult. Whereas with alluvium, you are guaranteed to hit pores.
Yes.
The pores are everywhere.
Yes, you will. Yes, you certainly will. And many of the aquifers, the sedimentary rock aquifers, all sedimentary rocks have pores.
Mm-hmm.
All of them below the water table contain water. Just the question is, are the pores big enough to let that water flow freely?
Mm-hmm.
But for instance, once again in Texas, the coastal plain aquifers, the high plains Ogallala aquifers extend over hundreds and hundreds of square miles.
Could you talk a little bit about the Ogallala Aquifer? It's something that comes up. I think that's maybe a pretty famous aquifer. How does that compare to the floodplain aquifers you mentioned earlier?
The Ogallala, of course, is not then confined to be near the river, and it's spread over much of Texas, parts of Oklahoma, Kansas, Nebraska. It's a huge aquifer. It's the breadbasket of the United States, and once they realized they could put wells down and pump them, they went from dry land farming and just pastures to producing huge amounts of crops. And it still is. However, in many places, they've pumped out water much, much faster than it goes in. The recharge rates to the Ogallala or the High Plains Aquifer are small, but the wells can be extremely productive. In some places, they've lowered the water so deeply that the wells are essentially dry. Mm. And in those places, the farmers have had to stop irrigating or go to dry land farming. Now, in some places, there still is plenty of water. Now, when I was in graduate school, and that was in the 70s, it was predicted the Ogallala would be dry by the year 2000. Mm-hmm. Well, some places are, but in other places, it's still producing like mad. So, once again, a tremendous aquifer, and once again, extending far to the north, and in places where they've irrigated over the Ogallala with nearby river water, the aquifer levels are actually rising. But that's in Nebraska. But in Texas, New Mexico, Kansas, Oklahoma, they're dropping.
So that would be a case of an aquifer where the recharge rates are low and the discharge is primarily pumping
by wells for irrigation.
Are there springs fed? Are there major springs fed by the High Plains Aquifer?
There are springs, but they're limited. Mm-hmm. And as they've dropped the water levels, those springs are drying up.
Another place that people may have heard of an aquifer or groundwater at least is the Central Valley of California. Have you ever done work associated with that aquifer?
Yeah, that's another extremely productive aquifer. And once again, also producing much of the vegetable crops grown in the United States. And one of the interesting things there is when you pump water out of an aquifer, you also reduce the fluid pressure. Mm-hmm. And the rocks can compress. And this causes land subsidence. And in some places in the Central Valley, the land has sunk land surface by 75 feet.
Wow.
Now, we also have that in Texas and in the Houston area, where Houston was being watered basically by waters from the Chico and Evangeline aquifers, the coastal aquifers. Mm-hmm. There, the land is sunk in some places over 12 feet. Mm-hmm. So the road and the San Jacinto Monument that used to be above water is now underwater. Mm. And so there was severe subsidence. And the solution there is to switch from using groundwater to using surface water.
So that's fascinating. Maybe if you've never heard of it before, you can actually, people can pump so much water out of the ground that the ground sinks. It's like...
Yes. And Long Beach Harbor, there was an oil field there, and there was not pumping water, but it was pumping oil. Mm-hmm. And the oil, as you pump oil out, if you take more oil out than goes in, hardly any is going in, the fluid pressures drop and the rocks consolidate. So there are places in Texas that the ground surface is sunk by 5 or 6 feet over a course of a few decades from pumping of shallow oil and gas.
And it seems like Houston, they don't need to be sinking at all. That's not good for flooding.
No. And to a certain extent, if the whole ground surface sinks, you're okay unless you're kind of close to sea level. Mm-hmm. And the water comes in. But unfortunately, it's not uniform. Mm-hmm. The ground sinks unevenly. In some places, it'll sink more than others. So even in places where you're not worried about the sea coming in, you're changing the surface topography. In areas that used to not flood by rivers are now flooding. And of course, when the subsidence is different in different places, we call it differential subsidence, and this destroys underground utilities and pipelines. So it's an issue even where you're not getting the ocean coming in.
Right. Yeah, it's a common theme, I think, with the interaction between civilization and Earth systems is that stability is good for civilization. It makes things simple. But when things change, then we have to think creatively and bad things can happen. And so I don't necessarily have a point, but it's interesting all the different ways that humans can change things that seem so unchangeable, like the elevation of the ground.
Right. It's obvious it was always been that way, correct? Well, no, as we measure these things and our measurements get better, we're finding this more and more. And of course, man, we know, is a major change of the earth landscapes. In our construction and building, we move more sediment now than all the rivers combined. So as we urbanize and as we went to agriculture, we changed the landscape. And now with urban sprawl, we're also changing it, but in a different way. And this is creating changes to our groundwater systems that we hadn't really predicted before.
This is sort of a whimsical or a little off-topic question, but you just made me think. Do you think in the future, so the rivers moving sediments, like if you studied the field of geomorphology, which is how landscapes change, you learned that rivers are the main process that affects landscapes. And so if humans are outpacing rivers, and rivers, the effects of rivers are recorded in the rock record.
Yes.
And lots of people study deposits from rivers to learn a lot of different things about the history of the earth. And so presumably, if humans are a similar scale of change as rivers, it's that also would be preserved in the rock record. It'd be very interesting to imagine an outcrop in the far future where you could say, oh, this is where people transition to agriculture because these rocks look this way. And this is where people transition to urbanization because of these things.
And people are doing that now. And yes, if you find in the sediments disposable beer bottles, you know that those sediments, when those sediments were deposited, so that was...
Okay, can we talk about the Edwards Aquifer? Maybe sure. When did you first hear about the Edwards Aquifer?
Well, any hydrogeologist has heard about the Edwards Aquifer, and you go back to the first book on groundwater was done in Germany in 1912, and Kyle even had a page on the Edwards Aquifer. So It's been known for a long time. And when I moved to Texas in 1982, there's just so many issues involved, and it's so interesting that I think any hydrogeologist in Texas is going to find themselves involved in the Edwards Aquifer in some ways. And I remember when I came here, and there was I started looking at the aquifer, and I presented a paper in 1996 at the International Geological Congress, and basically had the basics right. But as we started looking in more and more detail, we found more and more interesting things. I was also involved in a case where we were looking at could we artificially recharge the Edwards Aquifer to preserve spring flow in San Marcos and Comel Springs? And it turned out that we probably can, but it's going to be expensive, and we're going to have to change the way we do things. But it was very interesting. And the other thing when you're dealing with the Edwards Aquifer is a lot of people have strong opinions. And so if you, in Texas, I think it's Mark Twain said that, but whiskey is for drinking, but water is for fighting over. And if you're dealing with the Edwards Aquifer, there's lots of fighting about it.
What makes Edwards Aquifer so special from a hydrogeologist perspective? Why is it famous?
First of all, it extends over a long, narrow belt between the coastal plain and the hill country. It provides water to millions of people. It provides water to important springs, and all the springs, if you're going from basically from Salado through Round Rock, Austin, San Marcos, New Braunfels, San Antonio, Castroville, Uvalde, all of those towns, Del Rio, all where the springs were. So the springs actually determined where the people were going to live. And then, of course, as we've developed and urbanized, the demands in this water have become ever more. And we could probably still produce more water out of the Edwards Aquifer if we wanted to. But there are important springs that people don't want to go dry. And we have federally enlisted endangered species that we have to protect. We want to protect them. So we have to learn how to manage the aquifer much, much more efficiently. If you need more water, if you have water resources, if you need water for people, what can you do? You either have to, if more people are coming in, you have to become more efficient in how we're using it, or you have to bring in water from a distant source, or you have to be very clever about the source that we're using. We're going to have to do all of those.
It's like maybe being a company or some organization, your budget is just fixed. And but the company's growing, so it's an interesting conundrum.
That's exactly, and we're expected to double in population, I think, in 30 or 40 years. Those people are going to demand water, and we're going to have to find a way to provide it.
Going back to the sort of the basics of the Edwards Aquifer, you mentioned this narrow belt that sort of I-35 corridor parallels. I think it's fascinating. You can see on satellite imagery, look at Google Earth on the satellite setting, and you can see this crescent through the center of Texas of cities and greenery. That's called the Balcones Fault Zone. Can you talk about what are faults? What is the Balcones Fault Zone? What does that have to do with springs?
Right. If you look at Texas, we have the Gulf Coastal Plain, which is the flatlands basically between the Edwards Aquifer and the coast. And those are all rocks that have been deposited really since the death of the dinosaurs, in essence. Well, some a little before, but basically, since the dinosaurs have gone. Now, there are some deeper ones there too. But as you drive from the coast towards San Antonio, Austin, suddenly there's a line of hills. That is a fault, and there's a vertical, it's a slanting surface where towards the Gulf Coast, the land has sunk, and that forms the Gulf Coastal Plain and the Gulf of Mexico Sedimentary Basin, which is a tremendous oil repository. So much oil and gas produced there. And the Edwards rocks were deposited during the age of the dinosaurs. They are Cretaceous rocks, that's the term. They're limestones. They have holes in it. As you go further towards the coast, those rocks get deeper and deeper. But right near what we call the Balcones Fault Zone, they're exposed at the surface. And if you go further to the hill country, those rocks used to be there, but many of them have been eroded. So in the fault, as you go, the rock units, say from San Antonio or Austin, going towards the coast, are dropped down, and that's what the fault is. So it's a geological structure. It's a discontinuity. Basically, think of a piece of paper that's tilted. And on one side, the rocks have gone down, and the other side, they've gone down. Here, they've gone down towards the Gulf Coastal Plain.
Yeah, for people that don't think about sedimentary rocks, what you can visualize, those rocks were deposited as alluvium or other sorts of sediment, kind of like we talked about earlier, in big, broad sheets, basically. And then they turn into rocks. They become hard and brittle in the case of the Edwards rocks. And I actually heard that the reason the Balcones Fault Zone is there is because so much sediment is being deposited in the Gulf of Mexico that the Gulf is sinking under the weight of the sediment. And actually the Balcones Fault Zone represents where those brittle rocks are sort of breaking to accommodate that sinking.
Yeah, and lift it up. And the Edwards Aquifer and the days of the dinosaur, there was a huge inland sea. These were basically shell fragments and stuff that accumulated in that old Cretaceous sea all those many years ago. Now, and then where these rocks were re-exposed to the surface, they've been undergoing what we call karstification. The water being precipitating, picking up acids in the air and in the soils, are dissolving the rock and creating caves and caverns. And these creates zones, think of it almost like a huge water tunnel under that, of tremendously high permeability. And the water can flow in these units on the order of miles in a day.
So this is an example, Edwards is an example of how the geologic material really determines the properties of the aquifer. The Edwards rocks are, you mentioned limestone, and an important consequence or property of limestones is that they're relatively soluble compared to other kinds of geologic material. It's something that listeners may check out the podcast episode of George Vinny where we talk about this pretty much exclusively. But the long and the short of it is that these Edwards rocks can dissolve to create essentially massive pores.
You can walk through some of them, and there are cave systems you can tour here, and natural bridge caverns, underground space, just a couple of them, and but there's caves that have been explored all over this area, and that's one of the reasons this aquifer is, on one hand, very vulnerable to pollution, because water and whatever the water is carrying can get in there very quickly. On the other hand, because the water can flow through them so fast, they can basically flush out the contaminants much more quickly. So the Edwards, rocks deposited in a shallow sea during the age of the dinosaurs, and were buried and became not just carbonate shell mud, but a rock. And now they've been exposed, and they're eroding and dissolving and creating new pathways. They're being karstified. And so we have some of the largest springs in North America coming out of this aquifer, which is one of the reasons people have been so interested in it. And then we found there's all sorts of endangered species. What are we up to now? 20-some species that are either threatened or endangered that are only found in the spring systems or the aquifer itself, found nowhere else in the world. So it's just an amazing system, amazing aquifer.
Yeah, that's something that I would love to learn more about. Is that it's fascinating that Edwards Aquifer is actually hosts an ecosystem.
Yes, and we say we thought we keep learning things, and it turns out the aquifers are an ecosystem with different microbes and biota.
Mm.
In fact, in some places, the biota in a portion of the aquifer near what we call the bad water zone, the biota seem to be dissolving the rock, the microbes. And as we've looked at these things, we find more and more differences and new things. As kind of a sidelight, we did a study years ago in a karst system in Mexico, and when we sampled the walls, they found 7 new divisions of microbes that had never been seen anywhere else in the world. So we're just learning. We're kind of in kindergarten in this stage.
Would you say that the Edwards Aquifer is a particularly complex groundwater system?
That's a very good question. On one hand, it's very simple. We kind of know in general where the water goes in and in general where the water goes out. But once we start, the documentation of this is difficult. For instance, at the Edwards Aquifer up in Austin, there are streams that cross the aquifer, and there's places where years ago we injected dye into it, and they never came out at Barton Springs, because at that time we knew all the water in that portion of the aquifer came out at Barton Springs. We said, gosh, what happened to it? It must have been diluted, and so that we couldn't see it. Well, it turned out that there are other springs which are now mostly submerged, and the water in major portions did not go to Barton Springs. It went to a discharge at a completely different space. And the more we look at this, the more common that occurs. It used to be we thought that the rocks underneath the Edwards Aquifer, where to the west of us, have been uplifted. We thought they were separate, and now we find that they're connected to the aquifer in a way we had never predicted before. And looking at the flow paths, we can trace these with dyes and tracers. And I think this has been very important. It allows us to say these are the actual paths of the water. But, it's the details that are very complex, and we're learning more every decade.
From my perspective, I would say it's a complicated system in the sense that there's a lot of spatial heterogeneity or differences. So, if you're thinking about alluvium, it's basically a property that you measure in one spot, like the permeability. You can generally assume it's going to be the same in another spot, given, certain assumptions. But in the Edwards, it's not necessarily the case, because they're, like we were kind of talking about with cracks in granite, there's, you can measure the properties of, basically the properties of like the rocks that in one spot have totally different hydraulic properties than a rock right next to it that has a cave running through it. The cave will totally dominate the flow, but there's not really necessarily a good way to pinpoint exactly where a cave is going to be.
Although as we map them, we're learning more and more. Mm-hmm. But Logan, you're exactly right. In some places, you put a well down and you can't pump enough water out to water your cat. But in others, it's productive, really productive. Some of the wells are so productive that if you pump them, the water flows in so fast, you don't even see the water levels in the well go down. And so it's a tremendous range. And if you hit one of the really productive ones, you got all the water you could ever want. In fact, the biggest well in the world was in the Edwards Aquifer, the Catfish Farm well.
Wow.
That was the most productive well ever produced, as far as I know, anywhere in the whole world.
Wow. In hydrogeology, there's an interesting mix of like practical problems. You know, the very definition of an aquifer is sort of operational. It's related to how useful the water is. And so those kinds of things are well suited for like maybe an engineer skill set. But there's also like some fairly deep theoretical and abstract problems that are more well suited for someone trained as an academic scientist. Does that juxtaposition in your experience cause problems, or is there like a richness that comes from that?
You know, I think it's I think it goes both ways. I think looking at the practical aspects sometimes suggested here's an issue that we have to study.
Mm-hmm.
And on the other hand, the theoretical one says here's something that we have to study because we don't understand it yet.
Mm-hmm.
And so I think it works both ways. Now, sometimes the theory on how to analyze aquifer tests have advanced so much that we think we can, if we put a well in and we pump it, we think we can really predict how well it's going to work in the future,
Mm-hmm.
and how these things go. But looking at the practical issues sometimes raise, these are the theoretical issues we have to address. One of the tools we use to understand aquifers now are groundwater models. They're
Mm-hmm.
computer models.
Mm-hmm.
And when the computer models don't match the data we're seeing, the question is, what is it about the aquifer we don't understand?
Mm-hmm.
And so here, the practical numerical computer model to predict how much water we can pump, how much the water levels are going to drop, well, it kind of works. But when it doesn't work, this raises the most interesting questions. Why? What is it we don't understand? And this can then lead to new scientific understanding.
It's fun to, I'm happen to kind of enjoy reading popular science books and topics like like fundamental questions in physics and stuff, just because it's interesting. But something that I read about, with like high energy particle physics, for example, where people build giant collision, like that Large Hadron Collider. Something, a theme that I see a lot is, you'll have people that come up with theories. It'll be like some sort of model in some sense. Maybe it's a beautiful differential equation or something. But what guides that field is then you do experiments and see if the experiments like match the predictions of the theories. Is there an analogous process in hydrogeology?
Yes. I'm not thinking of the Edwards Aquifer, but one of the ones we have been looking at is karst that is formed by acids being released by volcanoes
Mm-hmm.
and magmas, which is the liquid lavas under the surface. And we think that there may be more of these than we know about because they form deep underground. And it's only till they're exposed that we can find them. And this is one the theory says we should be developing big cave systems in limestones at depth wherever there is volcanic activity. That's a prediction.
Mm-hmm.
Now, how do we verify that?
Mm-hmm. Mm-hmm. If you could communicate one idea perfectly from hydrogeology to the public, what would it be?
Oh boy.
In other words, what's like a concept you've employed in your career that it would make your job easier if everyone understood it?
Basically, groundwater flows from area of high head to low head, and we can apply mathematical models to solve the system, but we have to get data to understand the physical and chemical properties of that system. So I think we have the basic physical and chemical and mathematical concepts. But getting the data to put into them is something else. Now, that doesn't mean that our concepts are always right. For instance, one of the things that we've often ignore is the fact that water of different densities can sink. It can overturn. We call it convection, free convection. And we've kind of ignored this in many of our groundwater systems. But where we've had places where we've had, say, saltwater brines being deposited on the Earth's surface, it turns out these sink much more rapidly than we had predicted, because the heavier things sink. And conversely, we have lighter fluids that are hotter or less saline rising up. And we know basically physically how that works, but we don't know the effects on the aquifer systems yet.
And sort of a related hard question, is there sort of a concept you've employed in your career that you wish other geoscientists were more familiar with? Like maybe you give a talk and you get the same question over and over or something, then you wish...
Well, one of the ones, yes, was when we looked at the effects of urbanization in groundwater systems. And we find that water lines all leak, sewage lines all leak, storm sewers all leak, and we have always ignored these. Now, isn't it interesting that Waller Creek in the University of Texas campus flows even though it hasn't rained in months? And later people came in, looked at that, and chemically it said this water had all been in city of Austin water mains at one point. So that's one. Another one, which was we think that paving is going to reduce the amount of water going into the subsurface. Well, sometimes it does, but sometimes it actually increases it, because I haven't seen a pavement yet that doesn't have cracks in it. And so we find that the effects of man on the systems has been grossly underestimated. We understand if we pump and drop the water levels what that does, but we're also changing the structure of it itself. And so one of the things we talked about, you've talked about karst. It's got certain characteristics. It's got slow flow paths and fast flow paths. When you take an area and put a city on it, you basically make the subsurface, the shallow subsurface, act like karst. It's got everything. It's got sinkholes. That's where the storm sewers go in. It's got caves and conduits in the sewage lines. So once again, it's interesting if in Adelaide, Australia, we were looking at a place there, and there's a storm sewer. And the storm sewer always has water flowing in it, even when there haven't been any storms in months. And that's coming from the urban leakage. And so the storm sewer there is acting like a cave or conduit in a karst system.
I'm really glad you brought this up, because something I hear about a lot in my job here as a geoscientist is the question is posed often, and rightly so. What is the effect of different land use changes on, in our case, recharge to the Edwards? And I think for some reason or another, I think a lot of people have this intuition or understanding that impervious cover is sort of an issue, and that the more urbanization that happens, the less recharge you might have. But what you're talking about is almost, that's not necessarily, it sounds like the story is more complicated than that.
Actually, it's there's two things. When you pave things, when you get rainstorms, the flooding gets more intense because the water doesn't have a chance to sink in. And the other assumption was you reduce groundwater recharge. But studies have shown that that is rarely the case. In almost every place that we can find documentation. There's more recharge after you urbanize it than there was before. Now, it may be more polluted, could be, depends, but there's more. The only places where it's not is in very well-maintained cities with new pavement. They're really looking at it. But in some places, 50% or more of your water leaks in the water distribution mains before it gets to the homes. And the sewage lines, when it leaks, probably about the same. In fact, kind of interesting, somebody said that, and it's an ancient study when I started looking at this, that if the pipe is only leaking 6% of the flow, it's considered perfect pipe. So anyhow, why do the streams flow when it's not raining here? It's probably coming from our systems.
Very fascinating. Do you have a favorite textbook?
Oh, favorite textbooks. Well, I think it was my class notes was my favorite textbook, but there's and there's some really good ones. I liked Chief Tolman's book back in 1936 because he had a wonderful picture showing flow in pipes and stuff. But I like Conrad Keilheck's 1912 Grundwasser und Quellenkunde because that's the first one.
And is that the one where he mentions Edwards?
Yeah, he has a picture of San Marcos Springs in it from 1912. Amazing. Yeah.
Well, Jack, thanks so much for speaking with us. I hope we can have you on again sometime soon. Thank you so much.
And I would like to encourage any of your young listeners is to study geology and also take as much math, physics, and chemistry as you can and get out into the field. Get out and look at the rocks, look at the springs, look at the landscapes, and you'll find it's a very rewarding career personally, and it's going to be extremely important to our society in the near and in the far distant future. So thanks, Logan. I appreciate the opportunity. Keep solving these water problems here at the Edwards Aquifer Authority.
Thanks, Jack. I will do that.
All right, y'all. Well, thank you for tuning into this episode of the Recharge Zone podcast. Be sure to subscribe to our podcast on your favorite podcast hosting platform. Tune in to charge up your knowledge on all things Edwards Aquifer from the EAA.